In this video, we're going to introduce the method called calorimetry. Now, you may want to pay particular attention because one of the labs that you will need to do this semester involves some calorimetry measurements. So you'll need to know pretty much how a calorimeter works and what its data represent. Our learning goals in this video are to evaluate heat change and do so by basically measuring temperature changes. To get started, let's talk about heat exchange and a quantity that we'll call enthalpy. Whenever we have constant pressure conditions, we say that the heat is equivalent to a special thermodynamic function called enthalpy, which we use the label H to call it. You can think of H as standing for heat because when the pressure is constant, that's exactly what it is. Now, we want to differentiate between what happens in the system and what happens in the surroundings. And the two are complementary to one another, so it's important to understand that relationship. When a system gains heat or gains enthalpy, that means the surroundings must lose heat. In other words, the two of them are complementary. If one gains, the other one loses. If that one loses, the other one gains. So we can write down very accurately that the change of enthalpy in the system is going to be the negative the change of enthalpy of the surroundings. Now let's use a picture to try to get a better handle on this. Here's a couple of possibilities where we've got a hot system and heat is flowing out of that system into the surroundings. Now, what we would ordinarily be able to do, we normally cannot measure the temperature directly of the system very easily, but we can easily measure the temperature of the surroundings. So usually when we look for heat changes in a system, what we're really doing is measuring the heat change of the surroundings and inferring then what the heat change in the system must have been. So in this case, when the system gives up a lot of heat to the surroundings, it's going to raise the temperature of the surroundings. So we would see delta T of surroundings be greater than 0. The opposite case is when the system absorbs heat from the surroundings. In this case, heat is being taken out of the surroundings, added to the system, and in that case, the change in temperature of the surroundings is actually going to be negative. So things that, like cold packs that turn cold, they're turning cold because they're actually absorbing heat from the surroundings and are turning the surroundings cold, but the thing itself is actually endothermic. Now, in calorimetry, which is our express way of measuring heat changes, we have a particular strategy that is used. The first part of that strategy is we want to isolate the system that we're interested in and its immediate surroundings by insulating them from the rest of the universe. In other words, we don't want anything else to interfere with our measurement to spoil the accuracy of what we might get out of that measurement. Now we're going to determine the heat capacity of those surroundings, the ones that are right next to our system, because they're going to be the ones that either absorb or give up heat to the system. Once we have run our process, when we initiate it, we're going to measure the change in the temperature of the surroundings. And we're going to use that then to compute the enthalpy change of those surroundings. Since the enthalpy change of the surroundings complements the enthalpy change of the system, we can easily get delta H of the system. All right, so this is the basic strategy that all calorimetry experiments utilize. Now, the instrumentation they use is something called a calorimeter, and it's basically a device that measures enthalpy changes in an object or system, and it does so very simply. It's measuring a temperature change of a fluid medium that surrounds a system that's either giving up heat or absorbing heat from it. So this picture gives you a little bit of a clue as to what sort of components are present in a calorimeter. Now let's look at an example problem to see if we can figure out how this works. A substance is dissolved in water in a calorimeter, and the calorimeter has a heat capacity of 251. The initial temperature of the water is 23.4, its final temperature is 26.5. So what we want to learn is what was the enthalpy change for this solvation process. The solvation is the dissolving process of this substance in water. Now, let's be clear that the system is both the solute and the water. But in this case, we've got a very interesting situation where the surroundings also is the water. So the water is kind of playing a dual role here. It's part of the process that we're measuring, but it happens to be one of those rare cases where we can directly measure the temperature change that goes on there. So in this case, the enthalpy change of our calorimeter is going to be the heat capacity of the calorimeter times its change in temperature. We're given the heat capacity as 251 joules per Kelvin. We're given the initial and final temperatures, so those are listed here. So this enables us to calculate that the enthalpy change of the calorimeter, and therefore that is the enthalpy change of the surroundings around the system, is 778 joules. All right, now using that complementary relationship with the system, we would find that the enthalpy change of the system is now going to be negative 778. So that tells us that this is an exothermic process. The system is giving up heat, and in giving up heat, it's heating up the surroundings. That's why it has gone, the surroundings have increased in temperature from 23.4 to 26.5. I hope this makes sense, and we'll see some more examples of calorimetry in coming lessons.